Great. So I think I'll make a start by giving a quick overview of the course and how things are going to work. So let me begin by introducing myself. My name's Mark Bull. I'm a senior researcher at EPCC with interests in various aspects of parallel programming and high-performance computing. I'm one of the lecturers on our master's program in high-performance computing, and I'm also EPCC's representative on the OpenMP Architecture Review Board, which is the body that maintains the OpenMP standard. So we're going to have 4 sessions over this week and next week. So today, Thursday, and then Tuesday and Thursday next week. So in the first session, I will cover some of the basic concepts to do with shared memory programming, and then we'll start to look at some of the fundamental ideas in OpenMP and how those relate to the general concepts. Then on Thursday, we'll get into some proper syntax. We'll talk about parallel regions and work sharing directives. Then next week, focus on synchronization and a few further topics. And then I'll finish up with a couple of lectures, one of which is basically a tips and tricks session. So this is all the little bits and pieces that can catch you out or help you in practice as an OpenMP programmer. And then I'll talk about performance issues. So each session is going to run from 2 to 4 p.m. UK time, and we'll take a short break between the 2 lectures. So in terms of asking questions, the way we'd like you to do that, if that's okay, is to type your questions in the chat window, in your Collaborate window. So you can find that if you open the panel at the bottom right-hand corner of your window where the purple arrows are, there's then a speech bubble icon at the bottom, which gives you access to the chat. You can type in the text box at the bottom of that panel. I will keep an eye on that, and I will read out your questions before answering them. And that way, we don't have to mess around with everybody's audio, and then hopefully the questions will be clearly recorded as well. So the lecture notes for these are all available by link from. So the easiest thing to do is either to go to the ARCHER2 website under the training tab and then follow the link to the materials from the course page. But I will also just post that in the chat window here now for you. Okay, so if you follow that link, that should take you to a repository with all the lecture notes in. So this course includes the opportunity for you to do some hands-on programming, and unfortunately the new ARCHER system isn't quite ready for us to open up to user access. So we're going to give you accounts on our tier 2 cluster, which is called Cirrus. So which has 36 cores per node, so it's still quite a nice system for experimenting with OpenMP. We'll give you guest accounts. So the details for registration will be coming soon by an email. So we'll pass that on to you either later today or tomorrow and tell you how to sign up and get an account on Cirrus. So the idea is that you work on the practical exercises in your own time. And then if you have problems, please post on the course chat page. So again, you can find that by following the link from the course web page. And I, or possibly one of my colleagues, will be monitoring that regularly to keep up with you and answer your questions. But also, please feel free to help each other out if you see a question on there that you know the answer to. And then we will have a wrap-up session where I will answer any questions and talk through some of the practical exercises. And that'll be on Thursday, the 29th of October. And the guest accounts will be open for a bit longer than that. They'll be open for another week or so after the final wrap-up session. And I will post the full instructions for how to do the exercises and the source code, the template source code that you need on the course materials repository, and we'll let you know when that's available. Okay, so before we dive into the first lecture, does anybody have any questions? So will the sessions be recorded? Yes, absolutely. The sessions will be recorded. It'll take a day or two for us to get the videos up and posted. So yes, there will be videos available of all the lecture sessions. Great, thanks, Claire. So a preferred programming language. So OpenMP supports C, C++, and the practical example. I will talk about both. I will talk about the syntax for both all three, and effectively all three languages as we go along. And you have the choice when you do the practical exercises to either do them in C or in Fortran. So there's template code available in both C and Fortran for you. Okay, any more questions before we get going? Okay, great. So I will pause at various points and to invite questions, but please feel free just to go ahead and type at any point, and I'll keep an eye out for incoming questions. So what I'm going to do in this first session, I'm going to say a little bit about hardware so that we have a mental picture in our minds of the type of hardware that we're that we're targeting with shared memory programming. And then I'm going to cover the general basic concepts underlying threaded programming. So this really extends to other APIs apart from OpenMP, and basically talk about the general concepts. And then in the second talk, we'll start focusing on OpenMP specifically. So let me say something about shared memory systems to start with. So threaded programming is most often used on shared memory parallel computers. So what's one of those? So shared memory computer consists of a number of processing units, CPUs or cores, together with some memory. And the key feature of these shared memory systems is that there's a single address space across the whole memory system. So what does that mean? It means that every CPU or core is able to read and write all the memory locations in the system. There's really one logical memory space. And all the CPUs or cores refer to a memory location using the same address. So the conceptual model that we have here is really very simple. We have a collection of cores or CPUs or processors, and there is a single global memory which all the processors are connected to in some way. So that's, if you like, the conceptual mental model for a shared memory system. But in reality, hardware is actually much more complicated than this, and that complication can happen in several ways. The memory may be split into multiple smaller units, for example. There may be some cache memory, maybe multiple levels of cache memory present. Some of those levels may be shared between some subsets of the processors or cores. And the interconnect might have some more complicated topology. But nevertheless, if it's a shared memory system, then this single address space is still supported. And the result of that is that the hardware complexity can affect the performance of programs, but not their correctness. And so the hardware guarantees that a correctly written multi-threaded programming will execute correctly, but the details of the hardware can affect the performance. So just to illustrate some of the potential complexities that could occur, of course, real machines now have many more cores than this. We're seeing systems like the new ARCHER system has 64 cores per socket and 2 sockets per node. So looking at 128 cores in a shared memory node. So that's kind of where we are in terms of current hardware. But this is trying to illustrate some of the complexities that are going on here. So now, instead of having really a single memory, the memory may well be split up into different pieces. And typically what you have is that if you have multiple actual chips in a node, then each chip will have its own memory. And then each chip may consist of a collection of cores. So I've only shown 2 here, but as I said, you could have, these days you could have 32, 64 cores. And then each of those may have, their own level 1 cache memory. And there might be some shared lower levels of cache. So again, typically these days have 3 levels of cache memory, and level 3 is shared between some subset of the cores on a chip. And then we can have multiple chips multiple sockets inside a node. Again, so the typical number these days seems to be 2. And that's really for design and economic reasons. In principle, there's no reason why it couldn't be larger than that. In the past, we certainly had systems with 4 or even more sockets in a node. 2 just seems to be the right sweet spot in the current hardware. And these 2 sockets are interconnected in some way. So that means that, for example, this processor here up in the top right is able to access not only the memory attached to its own socket, but also all the memory attached to the other socket as well. So despite all this complexity, it appears to us, it appears to the programmer as though there's a single global memory and all the cores have access to it. And any copies of data that are made in the caches at any one time are completely transparent. So you don't see that. That's all hidden from the programmer. You can observe it in terms of performance, but it's not, doesn't appear in the programming API or in the programming language in any way. Are there any questions about that before I move on? The question is, can you run OpenMP on a distributed machine? The answer is essentially no. So OpenMP is really limited to shared memory systems. There have been some experimental attempts to support OpenMP and other shared memory programming models on distributed hardware, but without the appropriate hardware support, it really doesn't work very well. The experience has been that the performance is really very, very poor if you try to do it on distributed hardware. So it's not impossible, but it really doesn't work very well, and you won't find it widely supported. Okay, so Milena asks, what's the difference between SMP and NUMA architectures? Okay, so if I go back to this slide, so this is what would typically be described as a NUMA architecture, because each socket has its own memory. So there will be typically some differences in performance between, it will be faster and more efficient for this processor to access the memory that's attached to its own socket. It is for to access across this interconnect into the other memory. Whereas a sort of classical SMP design is more like this, where you only have a single memory. So if you just have half of this, if you just had a single node, that would be an SMP design. So if you had a single socket in the node, that would be an SMP design. Once you go to 2 sockets, then you typically have a NUMA architecture. And indeed, actually, some of the newer chips with very large core counts, they are even NUMA inside a single chip as well. So the new hardware that's coming on Archer, the AMD Rome processors, they have, so a NUMA region consists of a subset of the cores on a single chip. So I'll talk in the performance lecture at the very end about some of the performance impacts of NUMA on OpenMP programs and ways that you can deal with it. Okay, so Fraser asks, what determines how many threads you can run on a core? And there's an easy way to find this information. Okay, so I'll come on to this in the next slide. So if you'll bear with me and I haven't answered that, I'll please let me know. And Tom asks, can OpenMP be run on GPU and CPU on the same node as an alternative to OpenCL on CUDA? So the answer is yes, with some qualifications. So the latest OpenMP standards, so from 4.0 onwards, do support offloading to GPUs. It's similar in style to the OpenACC API, but it's different. Okay, it has different syntax, but has much the same functionality. There are still a relatively limited number of compilers that support that. It's getting better, but it's not necessarily everywhere. But the answer is yes, though I won't be covering that in this course, the GPU offloading material. Okay, so let me now talk a little bit more down at the software level. So the programming model for shared memory is based on the notion of threads. So what are these threads things? So threads are like processes, but the main difference is that by default, threads can share memory with each other, as well as having their own private memory. So typically, if we have multiple processes running, then they have separate logical memory spaces, and you have to do something special to make processes share memory. Whereas threads, by default, have some shared memory, some shared section of the address space that they can all access. So in this model, there are essentially two types of data. There's some shared data that can be accessed by all threads. And there's some private data that can only be accessed by the owning thread. But it's important for me to stress that this distinction is very much a software distinction. So shared and private data is nothing to do with main memory and cache memory or any sort of special memory in the hardware. It's really just a logical separation of the address space such that there is some part of the address space which all threads can access, and then every thread also has a part of the address space which only it can access. So to do useful parallel programming, different threads can follow different flows of control through the same program. So another way to think about that is that each thread has its own program counter. So each thread has its own notion of which instruction in the program it can access, which instruction it's going to access next. Okay, so Lee asks, is there any limit for private memory? So typically, private memory is implemented as a per thread stack. And there is usually a default limit on that. But there are ways that you can change it. And I will talk about that in a later lecture. Okay, and to get back a bit to Fraser's question, so we usually think about running one thread per CPU core. Okay? Doesn't have to be, could be more, and a lot of modern hardware has hardware support for multiple threads per core. So this is what Intel call hyperthreading, or more generally called simultaneous multi-threading. So where the hardware has efficient support for multiple threads per core. In practice, that doesn't always help, and in fact may not be beneficial. And depending on how HPC systems are configured, then hyperthreading or simultaneous multi-threading is often disabled by default. And you have to turn it on explicitly. So usually via some options in your batch job, you request simultaneous multi-threading to be enabled. However, the operating system is perfectly happy to have many more threads executing than there are actual hardware cores or hardware threads available. And the operating system will time slice your threads as you know, in the usual way. So it just does the same thing as it does for processes. It will try to give threads some fair share of the hardware resources. That's usually not what we want for performance, though. So for performance, we really want this one-to-one mapping of threads to cores, or possibly to hardware threads. So to answer Fraser perhaps a little bit more specifically, you have to know, you have to essentially read the documentation for the system that you're working on, figure out how many cores do I have, how many hardware threads does each core have, and are those enabled by default or not? And then that can help you determine how many threads how many software threads you're going to run. Okay, so just to illustrate this with a diagram, so suppose I have 3 threads, a green thread, an orange thread, and a purple thread. Then each thread has its own program counter. It has its own private data, but all the threads have access to some shared data. I'm going to move on and talk about thread communication here. So in order to have useful parallel programs, threads need to be able to exchange data with each other somehow. And the way that they do that is by reading and writing the shared data. So if I want to transfer some value from thread 1 to thread 2, then thread 1 can write the value into a shared variable. Let's call it A. And then at some point later, thread 2 can read the value from that same shared variable. And that's achieved the exchange of data. So if you've done any MPI programming, any message passing programming, this is a very different model. There is no notion of messages in the threaded programming model. So threads don't send messages to each other. They simply communicate by reads and writes in the shared data. Okay, so let's try to illustrate this with a little diagram here. So suppose I have my two threads, thread 1 and thread 2, and then I'm going to show so little bits of program in here. And so each thread has its own private data, and then here's the shared data down at the bottom here. So suppose the first thing that happens is that thread 1 writes a value into value 23 into a variable called myA, and myA happens to live in thread 1's private data. Okay, so how we arrange that exactly depends on the programming API, and we'll talk a lot about how that happens in OpenMP as we go along. But let's just take that for granted now. So then if thread 1 wants to transfer that value to thread 2, it could then say copy that value into a shared variable called A, which happens to live in the shared data space. So that would also have the value 23. And then at some point later, thread 2 could read the value from A and then do some computation with it, like add 1, and store the result in its copy of myA, which lives in thread 2's private data space. So we can see the distinction here between the shared and private variables. So for myA, each thread has its own copy of myA, and they are separate from each other and can have different values. But both threads, when they reference A, which is in the shared data, they see the same copy, and that has a single well-defined value at any given time. Any questions about that? Okay, so we move on and talk about synchronization. So by default, threads are executing asynchronously. So that means that each thread proceeds through the program instructions independently of other threads, and that may happen at different rates. So we have no guarantee that even if threads are executing the same piece of code, that they are executing in the same part of the code at the same time. So this means that we need to ensure that actions on shared variables do actually occur in the correct order in some way. So for example, we may wish to ensure, in that previous example, we have to ensure somehow that thread 1 is going to write the variable A before thread 2 reads it. Or we can have other patterns as well, because we tend to reuse memory location. We might want it the other way around. We might want to ensure that thread 1 reads the old value in A before thread 2 writes something new into it. And in this context, it's important to realize that updates to shared variables, so if you write something like A equals A plus 1 and A is a shared variable, then things like that are not atomic by default. So if you think what's really happening by the time we've translated that program, by the time we've compiled it into machine code, then that requires at least 3 instructions to execute. There's going to be a load of A, and then there's going to be the add instruction, and then a store instruction. And so if 2 threads try to do that in quotes at the same time, in other words, without any synchronization, then those instructions may be interleaved in time in such a way that one of those updates gets overwritten and lost. So what do I mean by atomic? So I mean atomic is a single indivisible action, so that the result appears to other threads immediately, and this kind of interleaving cannot happen. Another way of thinking about it is it's not atomic means that it's that action is not happening one thread at a time. There's no guarantee that one thread at a time is performing that action. So again, hopefully it's clearer with a little example here. Okay. So now I'm really thinking about hardware rather than the logical division of memory spaces here. So I'm thinking about hardware. So instead of threads, I'm really thinking about cores here. Okay, so suppose I have two different cores and I have a thread running on each, and each of those threads, excuse me, each of those threads wants to add one to this shared variable in memory down here. So the variable has the initial value 10, and then both threads are going to try to add one to it. But here's what might happen without any synchronization. So first thing that happens is that core 1 loads A. So that actually takes, so what happens in the hardware is that makes a copy from memory into the CPU registers, which is the local storage on the core. And then core 2 might also load A, so it also gets a copy. And then core 1 does the addition, so the addition only operates on the registers, so core 1 now has the value of 11 in its register. Core 2 does the same. And then core 1 stores the value back into memory. So the value in memory now has the value of 11. And you can probably see what's going to go wrong here now. So if the last thing that happens is that core 2 stores the value back into memory, then we have a problem. Okay. Started off with the value 10. Had two threads, both tried to add one to it, and we ended up with 11 instead of 12. So in order to ensure the correct result here, we have to do something that makes sure that that kind of interleaving can't happen. So for example, that all these instructions from core 1 happen, including the store, before any of the instructions, including the load, happen on core 2. And so if we guarantee that, then we will guarantee getting the correct answer. But that does not happen by default. So multiple threads trying to update shared variables without any synchronization, without us taking care as a programmer of any synchronization is bad. So just a bit of terminology here. So this problem is an example of what's called a race condition. So a race condition occurs when multiple threads access the same memory location without any synchronization, and at least one of those accesses is a write. If all the accesses are reads, then we don't have any problem because no values are being modified. So that's fine. But if at least one access is a write, then we have a problem. And without synchronization, different time orderings of those accesses may happen, and that may possibly result in non-deterministic behavior. So we end up with this extremely nasty property that if you run the same program with the same inputs, you run that twice, you might get different results. So that's a very nasty type of bug. It's a completely different sort of bug than what we're used to in sequential programming. And it's not reliably detectable by conventional software testing procedures. So you can't easily just write, for example, unit tests to test for race conditions. because you might be in a situation where you run your test 99 times and it succeeds, and then you run it the 100th time and it fails. So it's particularly unpleasant, and we have to try and do our best to avoid introducing them in the first place. Having said that, there do exist some tools which will help you to try and detect whether you've got race conditions in your multi-threaded programming, but they work very differently from conventional testing or conventional debugging. Any more questions about that? Okay, so the next concept, okay. So example of how to test for race conditions. Okay, so there are tools. So particularly Intel produces a tool called, which nowadays called Thread Analyzer, I think. They keep changing its name. And the way those tools work is what they essentially do is you run your program, and it basically records every memory access made by every thread. So it takes a trace of all the memory accesses in your program, and then it does some post-processing on that trace to look for problems that might have occurred. Okay, to look for accesses to shared variables that are not correctly synchronized. So that's how that type of tool works. Otherwise, you can just run your program lots of times and cross your fingers that you did enough testing. It's not really that great. So it's also useful to be very careful. Yeah, so you need to think quite carefully about how you're going to test in this situation. And yeah, defensive programming is a big part of this. And so trying not to introduce them in the first place. But it is tricky, and that's probably the feature that makes threaded programming the hardest. That's the biggest drawback is the possibility of race conditions and the difficulty of testing for them and detecting them. Good. So tasks. So the idea is quite simple. A task is just a piece of computation which can be executed independently of other tasks. So essentially, that's our job as parallel programmers, is to try and identify tasks in the program that can be executed independently and therefore in parallel. So in principle, what we could do is essentially to, if you could think about creating a new thread to execute every task. And that would be so logically correct, but in practice that can get too expensive, particularly if you have a large number of very small tasks where it was small as in terms of execution time. So instead, what we typically tend to do is try to decouple the notion of tasks and threads. So what we can arrange for is tasks be executed by a pre-existing pool of threads. So typically what would happen is that we create a fixed number of threads at the beginning of the program, and that's probably chosen depending on the number of hardware resources that we have, number of cores available. And then what happens is that tasks are submitted to the pool, and some thread in the pool will execute the task. And at some point in the future, we have some guarantee, some way of checking whether the task is completed or not. And in addition to that, so the tasks may or may not be ordered with respect to other tasks. So it's possible that we can identify tasks which have some dependency on other tasks. So for example, if one task writes some piece of data, another task needs to read it, there's a dependency, and we have to make sure that the tasks execute in the correct order. So OpenMP does have support for this task-like approach to programming. I'm not going to talk about it in this course. It's not used that much. But there are some good use cases for it, but it's used relatively little compared with some of the core features which I'm going to cover in this course. But nevertheless, the concept is useful, and we will see things that do behave a bit like tasks anyway. So Alessandro asks, can you change the number of threads while computation is running, like rebalancing? So the answer is, in OpenMP, yes, but in a limited way. And we'll talk about that in the next lecture. So if you don't mind, I will park that question and come back to it. So in general, in threaded programming APIs, the answer is yes. You know, some of the more low-level threaded APIs like POSIX threads or C++ threads, for example, you can just go ahead and create a thread or destroy a thread at any point you like. OpenMP is more structured than that. So it has a nested fork join structure which is imposed on you. You cannot just create and destroy threads whenever you want in OpenMP. So I think that hopefully that answers that next question as well. So yeah, it'll be easy to understand once we start talking in the next lecture about OpenMP specifics, about how that works. In a high-performance computing context, you almost never want to do that because you have a fixed dedicated hardware resource, and you simply want to use as many threads as you have hardware resources and keep that number fixed for the lifetime of the program. So that's by far the most common use case in a high-performance computing context. Okay, that doesn't necessarily apply to all other computing contexts where you might want to use threaded programming, for sure. Okay. Changing the number of threads can be used to do some load balancing, but typically there are better ways of doing that. So it's a rather cruel and there's usually better solutions provided by APIs like OpenMP for doing load balancing between threads, which don't involve changing the number of threads that are running. Okay, so parallel loops. Loops are the main source of parallelism in many applications, particularly in the scientific computing field. So the concept here is very simple. If the iterations of a loop are independent, in other words, they can be done in any order without affecting the result of the computation, then we can share out the iterations between different threads. So example, if we have a loop like this, which just forms the sum of two vectors, then it doesn't matter what order we do those additions in, we're going to get the same result. So suppose, very simple example, if we had a loop like this with 100 iterations, 2 threads, we could do the first 50 iterations on one thread and the second 50 iterations on the other thread. Actually, in practice, with such a simple loop body and 100 iterations, there's no way that you're going to get useful speed up from that. In practice, you would need something of the order of 100,000 iterations, and in reality, in order to make this worthwhile splitting up between threads. So what's the task here? Well, okay, if you like, you can think of a single iteration, single addition as a task, or maybe a set of iterations. So you can maybe think of groups of 50 iterations as a task here. And that's what's being assigned to different threads. And the final concept I want to introduce you to in this session is reductions. So a reduction is an operation that produces a single value from associative operations like addition and multiplication, maximum, logical and, logical or. So for example, addition is by far the commonest use case, followed by max and min, and all the rest are sort of ones that you almost never see. So addition is the really common case. So what happens, suppose we want to form the sum of the elements of a vector into a scalar variable b, like this. So think about what we would do. So suppose we make b a shared variable as well as a, and then we try to split up the iterations of this loop between different threads. Okay. Well, then we have a race condition. Okay. Exactly the problem that I showed you before, where you would have multiple threads all trying to update the same shared variable without any synchronization. So if we synchronized it and allowed only one thread at a time to update b, well, then we would get the correct answer, but we would remove all the parallelism. In practice, it would actually go slower than the sequential version. So that's not a good answer. So the solution here is fairly obvious. What we would like to do is to have each thread accumulate a partial sum in its own copy of b, and then have those copies added together at the end of the loop. So if the number of operations is much larger than the number of threads, then most of those operations can proceed in parallel, and there are a small number of operations of order of the number of threads rather than of order of the number of iterations, which have to be synchronized at the end. So this kind of pattern, think about in a case where n is 1,000,000 and the number of threads is 20. Okay? So then you would have you'd have 1,000,000 minus 20 things going on in parallel, and or a million minus 19 things going on parallel, and then you'd have 19 synchronized additions to add up the 20 copies at the end. Okay, any more questions? Well, thanks for all the questions, by the way. That's really good. It's really great to see, and it's so nice to have questions to respond to. It's fantastic. Okay, so in that case, I suggest that we have a short break for 10 minutes, and I'll start again with the next lecture at 3:10 UK time. Good. So now going to talk more directly about OpenMP and how the features of OpenMP map onto the general concepts that I've just talked about. So I'll cover some of the basic concepts in OpenMP. I'll say a little bit about the history of OpenMP, where it came from and where it's at now, and then some practical stuff about compiling and running OpenMP programs. So what is this OpenMP thing anyway? It's an API that's designed for programming shared memory parallel computers. Okay, no surprise. It uses the concepts of threads and tasks that I've already talked about. It's a set of extensions to Fortran, C, and C++. And those extensions consist of three things. So most importantly is compiler directives, which I'll say more about in a minute. There are also runtime library routines, and there are some environment variables. So a directive is a special line of source code which has meaning to only certain compilers. So it's a mechanism for extending base languages like C or Fortran. And the directive is distinguished by what's called a sentinel at the start of a line. So the sentinel is just a special sequence of characters that says that this is an OpenMP directive and not a line of normal C, Fortran, or C++. So for OpenMP, sentinels are in Fortran, $OMP, and for C and C++, #OMP. So why are they done like this? Well, it means that the OpenMP directives are ignored if the code is compiled just as regular sequential Fortran C or C++. And so that works in Fortran because OpenMP directives start with an exclamation mark. So a plain old Fortran compiler will treat that, without OpenMP enabled, will treat that as a comment and ignore it. And in C and C++, this is a preprocessor directive. And the way the preprocessor works is that if OpenMP is disabled, then any preprocessor pragma with OMP in it will be ignored as well. What this does is that it gives you, at least it helps you a lot in being able to write a single source code base that functions correctly both as a standard sequential program and as an OpenMP parallel program. Okay. So this feature isn't necessarily enough. Particularly if you have runtime library calls, then you also have to do something to take care of those and make sure those are conditionally compiled. But it helps. It goes a long way to helping you do that, and that's a very useful feature from a software engineering point of view. It's very convenient to be able to have a single source code base that acts both as a sequential program and as a parallel program, and you don't end up having to maintain two separate copies. So that's the reason why it's done like this. So now I'm going to talk about parallel regions. So a parallel region is the basic parallel construct in OpenMP. And in fact, it's the only way to get parallelism in OpenMP. So a parallel region defines a section of the program. And what happens with OpenMP is that the program begins execution on a single thread. So when we start an OpenMP program, it behaves just like a normal sequential program. It's executing on a single thread, and that's called the master thread. When the first parallel region is encountered, well, at least logically, the master thread will then create a team of threads. So this is what's called a fork-join model of parallelism. So at least logically, we don't have all the threads executing all the time, that only have the additional threads inside the parallel regions. And what happens is that every thread, including the master thread, executes the statements which are inside the parallel region. And at the end of the parallel region, there's a synchronization point. The master thread waits for all the other threads to finish executing that section of code, and then the master thread carries on executing the next statements in the code on its own. In practice, creating and destroying threads is expensive. So what most OpenMP implementations do is that they will create threads either at program startup or when the first parallel region is encountered, and keep them alive and use them for subsequent parallel regions. But that's down to the implementation. So at least logically, threads are created and destroyed every time we have a parallel region. So what we have here, okay, so here's a sneak preview of the syntax, and please ignore the blue boxes here. So in Fortran, the parallel region is denoted by the OMP parallel and end parallel directives. So the code inside here is the parallel region. In C, C++, it's the block of code in braces following the #pragma OMP directive. So what happens? So in either case, we start the program running, then we start with single thread. So that's the master thread executing on its own. It's called the sequential part of the program. And then when we get to the first parallel region, at that point, then we get parallelism. So in this case, I've shown a total of 8 threads. So that's the master thread plus 7 ones. And what happens is that all those 8 threads execute this block of code inside here. At the end of the parallel region, the master thread waits until all the other threads have also reached this point. Then we're back in the sequential part of the program, so we're outside parallel region. Now we're back to the master thread executing on its own here. And then we can repeat this process as many times as we like throughout the lifetime of the OpenMP program. So, an OpenMP program running one might execute millions of parallel regions in its lifetime. So going back to the point from earlier, we can see that there is this structured way of creating threads in OpenMP. It's possible to have nested parallel regions. So once we're inside a parallel region, a thread can also create a new team of threads by itself. But nevertheless, we still have this fairly rigid structure of the parallel regions where threads are created and logically finished at the end. The question is, will it affect performance by creating and destroying worker threads very often? So the answer is yes, it would. And what implementations typically do is actually keep threads alive. Okay, so typically what happens is that certain number of threads will be created at the start of the program, and those will be kept alive. So the actual kernel threads will be kept alive and will be used for every subsequent parallel region. Now, it's perfectly possible to change the number of threads between parallel regions. So different parallel regions can execute with different numbers of threads. And in that case, it might be necessary for the OpenMP implementation to then create some more threads. Okay? It might not have enough. Alessandro asked, do we need to keep them alive manually, or OpenMP does that automatically? That's entirely automatic. Okay, that is down to the implementation what it does. There are ways to hint to implementation as to what to do with threads in between parallel regions. So the implementation so it's probably not going to actually destroy threads between parallel regions, but it has a choice of whether it keeps them alive and consuming CPU cycles, or it could put them to sleep and wake them up again. So keeping them alive means that then starting the next parallel region is very quick, but that consumes CPU resources in the sequential part of the program. So on an HPC system, you may not care, because those hardware resources that those threads are using are not really available for anybody else to use anyway. So they're yours, and you might as well use them to keep the thread spinning so that you can restart them very quickly. In other situations, you might want to be friendlier to other processes on the system and to allow those threads to go to sleep during the sequential part of the program. So there are mechanisms where you can at least hint to the OpenMP runtime as to what behavior you would like. But in the end, it's actually down to the implementation to do the right thing. Okay. So again, Lee asked, we go from parallel region to sequential region. How do you keep those worker threads alive? I said, that's down to the implementation to do it for you. Okay? And there are these mechanisms to give it a hint as to what you want done. But you don't have any direct control. Yeah. let's now think a bit about shared and private data. So when we're inside a parallel region, then variables that are accessed can either be shared or private. So that behaves as you'd expect. All threads see the same copy of shared variables, and all threads can read and write them. And each thread has its own copy of private variables. And these are supposed to be invisible to other threads. As I say, it's supposed to be. That's something that's mandated by the specification, is that you are not allowed to try and access another thread's private variables. So in practice, there's probably nothing very much stopping you from doing this. Okay? So you could, in principle, have a private variable, take its address, store that in a shared variable, and then another thread could read that and then try and dereference and access memory. And in most cases, that will probably actually work. But it's very, the behavior is unspecified. You're not guaranteed that's going to work on all implementations. And it's just crazy madness. Okay, it would be insanely bad coding style to try to do that. And so, if you ever think about trying to do that, then don't. So you're not writing a correct OpenMP program if you do that. So private variables can only be read or written by its owning thread. So for shared variables, then the storage that's visible inside the parallel region is exactly the same storage that the master thread has access to in the sequential part. So that really is absolutely the same memory. Parallel loops. So in a parallel region, then by default, all threads are executing the same code. So we can do a lot with that, but for parallelizing loops, that turns out to be not terribly convenient. And you'll experience that in the first of the practical exercises when you come to do it. And so OpenMP also has directives that indicate that work should be divided up between threads inside a parallel region rather than being replicated. And in OpenMP, this is called work sharing. And we'll cover work sharing on Thursday after we've done parallel regions. Because loops are the main source of parallelism in so many applications, OpenMP has extensive support for helping you to parallelize loops. So for example, there are a number of options which control which loop iterations are executed by which threads, and how the load balancing is done if you want to try and load balance them, and so on. However, it's up to us as programmers to ensure that the iterations of a parallel loop really are independent. So just to emphasize that OpenMP will not check that for you. So OpenMP is not an auto-parallelization tool. It will not do anything to check that the iterations of the parallel loop are independent. It'll just try to parallelize it anyway. And if you got it wrong, then there may well be race conditions or other bugs involved. There is a bit of a limit to what you can do with this. So effectively, only loops where the iteration can be computed before the execution of the loop begins can be handled in this way. If you have parallelism in while loops or other situations where you don't know, or you have a case where you would break out of a loop at some point, according to some condition, then you can't do it this way. There are other mechanisms in OpenMP for handling that case there. In terms of synchronization, so there are really sort of three main ideas that OpenMP uses. There are others, but these are the main ones that are mostly used. So the first one, and by far the most common one, is a barrier. This is a full synchronization point between all the threads. So all the threads must arrive at a barrier before any thread can proceed past it. And that's what's happening. We've already seen that. That's what's happening for example, at the end of a parallel region. And that's what also happens by default at the end of a parallel loop as well in OpenMP. So if we have a parallel loop, then all the threads wait until all the iterations have been completed before proceeding to the next piece of code. Second one is a critical region. So a critical region is a section of code which only one thread at a time can enter. Okay, so it doesn't specify the ordering in which threads will enter this section. It just guarantees that only one thread can be executing that piece of code at a time. So that's exactly what we need if we want to do some modification of shared variables to prevent race conditions due to the kind of update pattern which I already talked about. And then thirdly, there's kind of a special case of that, which is atomic access. So this is an update or a read or a write of a variable which can be performed by only one thread at a time. So that's really kind of a special case of a critical region which just consists of an access to a single variable. A general critical region can have any arbitrary code in it and access any memory it likes. An atomic access is a special case which just refers to the access to one memory location. And the reason that's separate is essentially it's an optimization. It can be implemented typically on modern hardware. Atomic accesses can be implemented much more efficiently than general critical regions. And so we'll talk more about those next week. Okay, any questions? Okay, so a very quick history lesson on OpenMP. So the reason it came into existence was that historically, and by historically I mean sort of back when I started doing parallel programming in the early 1990s, that's like 30 years ago, this style of programming with shared memory directives already existed, had done for quite a while. But there was no standardization. So every vendor, every hardware vendor provided essentially their own compiler with a different API for doing this type of parallel programming. It was mainly directive based. At that time, it was almost all for Fortran. There wasn't much support for C or C++ at all. And that was okay, but it made it very hard to write portable code. You had to, every time you moved your code from one system to another, you had to rewrite all the directives. So that was the kind of the motivation for standardizing these things. So OpenMP forum was set up by a bunch of companies, some of which still exist in some form and some of which don't anymore. But now it includes most of the major vendors. So people like Intel, IBM, Cray, AMD, those kind of organizations, those kind of companies, as well as some academic organizations like big US government labs and some places in Europe, so including ourselves in EPCC. So the first Fortran standard came out in '97 with some revisions in the next few years, and then sort of in parallel with that, or just about in parallel with that, it's also the C++ standard in '98 and revisions to that. So at that point, those of us who were working on the standard realized really that it wasn't a great idea having two separate documents for the two different base languages, because in places they said the same thing in different ways, and in places they actually contradicted each other. So as from version 2.5, everything was combined into a single document. And then since then, there have been various extensions. So version 3 added some new features, including tasks. And then in version 4, the support for accelerated offloading, so offloading to GPUs, was introduced. And that's been revised and extended. So the latest version is 5.0. It was released a couple of years ago. 5.1 is due out next month. So in terms of most current compilers, so most current implementations comply with at least 4.5. Some of them are full 5.0 at the moment, except for the offloading features. Okay, so that has somewhat less widespread support. So not every compiler supports offloading to GPUs. So for example, the Intel compiler currently is in the process of having that added, but you can't use the Intel compiler for that for the moment, for example. Okay, a couple of resources. OpenMP has its own website. So in particular, you can download the full language specifications from there for free. They are very big and long, as standard documents tend to be, and there's a lot of technical terminology to get to grips with. So if you do want to, then by all means feel free, but it does take a bit of time to get into the terminology and understand what's really going on in there. In terms of, if you like textbooks, then there's a pair of textbooks with not quite, but an overlapping set of authors, which so the first one covers essentially the basic features, which I'm going to cover. So up to version 2.5 is really what I'm covering in this course, and then there's the second book, which covers sort of version 3 and beyond, version 3 and 4 really. Okay, just to finish up with then, so practical stuff. How do you compile and run OpenMP programs? Well, certainly in the high-performance computing world, then and also in the desktop and laptop world, OpenMP is built into most of the compilers you're ever likely to use nowadays. So to compile an OpenMP program, you need to add a compiler-specific flag to your compile and link commands. So it varies between the compilers. So for example, it's -f OpenMP for GNU compilers and Clang, and now for Cray's C and C+ compilers, which are essentially Clang now. -h OMP for Cray Fortran, -MP for Flang, -q OpenMP for Intel compilers. So you just have to read your compiler documentation and figure out what the right flag is to add to enable OpenMP compilation. And then the simplest way to determine the number of threads which is going to be used is by setting an environment variable. So this is a standard environment variable across all implementations. So this is, it's called OMP underscore num underscore threads. So what you do is you would typically set that to a value before you run the program. And that's the number of threads that will get used for every parallel region. There are ways to override that once you're inside the program, but by default, it will use the value in the environment variable. And then you can just run it in the same way as you would a sequential program by typing the name of the executable. So OpenMP doesn't require any special launch program, so it's different from MPI. There's no equivalent to MPI run or MPI exec or a launcher application like that. You just run it in the same way as you would a sequential program. Okay, so once you get, so I'm kind of running ahead of ourselves here because you don't have access yet, but the very first thing we'll get you to do is just a very simple hello world example to make sure that you're able to compile and run a trivial program and use the environment variable to vary the number of threads that execute it. Okay, good. Does anybody have any more questions? Okay, so as I said, we will get the details of the of registering for an account out to you either later today or tomorrow, and ask you if possible if you can try to do the registration this week. So unfortunately, in common with a lot of HPC systems these days, there is two-factor authentication and SSH keys to manage. So good to just spend a little bit of time making sure that you can get all that sorted out in order to get access to the system. It will provide you with all the instructions for doing that. And then I'll also let you know when the practical exercises are available. Again, that should be either today or tomorrow. And so once you get onto Cirrus, then you can get going. If you have any problems, there is a chat page linked from the course webpage. So please use that as your sort of first point of contact. If you have any questions, I say either about getting onto the system or about doing the exercises themselves, and we'll keep an eye on that and try to respond as quickly as we can to any questions. Great, so thank you very much for your attention today. I'll speak to you all again on Thursday. And thank you very much for all the questions and some really nice discussion points there. So thank you very much for that.